All right, so we are in section 12.5, day 2, equations of lines and planes. Today, we are going to talk about some of the applications, specifically the distance from a point to a plane, the distance between two parallel planes, and the angle of intersection of two planes, and the line of intersection of two planes. So we've got 4 different things that we're going to talk about. We'll do this in a couple of videos. The first video we're pretty much just going to spend on distance from a point to a plane, and then we'll do the other 3 in the second video. So distance from a point to a plane. Excuse me, let's go ahead and just kind of sketch. Got ourselves some kind of a plane here. It's kind of floating in space. And we're going to have some kind of a point up here. Okay, that's the point that we're interested in finding, the distance from that point to the plane. So we're going to call that point, I guess we'll call it P1. So it'll be x1, y1, z1. So that'll be the green point up there. We're trying to find the distance from that point down to the plane. But here's the thing. If we happen to know any one point on the plane, so the point could be anywhere, it would be really nice if that point was directly below. Like if the point extended down to here and it was perpendicular to the plane, man, that would be perfect. But more than likely, we're not going to know that specific point. If we did, then we would just literally do a distance formula between 2 points. But we don't necessarily know that. So we're going to call this point, we'll call it P0, because it's going to be at a point actually on the plane. So x sub 0 or y0, z0. So what we do know is that we can find a vector which goes in between the 2 points. So we can find a vector here. And that vector, I guess we can just call vector B in this case. We'll call that vector B. Would be the differences in the points. So it would be like x1 minus x0, y1 minus y0, z1 minus z0. That's vector B. Excuse me. Ultimately, what I'm really interested in here is this distance. We'll call that distance D. That's what we're trying to find. I know that the equation of a plane in general is AX, I'm going to slide this down a little bit, is AX plus BY plus CZ plus D equals 0, or if you wanted to move the D to the other side, you could, depending on how you write it. But that's the general form of a plane. I also know that coming perpendicular to the plane is a normal vector. So that would be a normal vector, and we'll call that N. And we know that the normal vector is the vector A, B, C. And that comes right from that equation of a plane that we developed. Okay? What I also know, is that there's an angle in between those 2 things right there. Okay, I can extend that vector up if I really wanted to, because remember, I can put a vector anywhere. I could extend the vector up to here, and I could also extend the blue vector if I wanted to, so that it starts here and go, oops, that doesn't look right. Whoa. Okay, stop. There we go. So I could extend, go away. I could extend the blue vector like this, and that angle right there is the same thing as the angle on the other side. So hopefully you can see that that really is the angle in between the two vectors. I just didn't extend the vector from the normal vector all the way up, but you could do that just to show you that the two angles are the same. They are vertical angles. All right. But what I do know is, because I'm trying to ultimately find that distance d, what I do know is that the cosine of the angle is going to be the adjacent over the hypotenuse. And if you think about it, these two things actually do form a right triangle from there, right? If you kind of sketch between the dot and the base of the normal vector. Cosine is going to be the adjacent, which is d, over the hypotenuse. Well, the hypotenuse is a vector itself right now, so we'd have to take its magnitude. And that would be the cosine of the angle. So what I could obviously do then is, to solve that for d, I could multiply both sides by the magnitude of b. So we're going to get that d is equal to magnitude b cosine of the angle in between. And while that is a formula that we could use, it's not going to be extremely useful in developing the distance formula. Now what I can do with that is I can take and I can multiply the magnitude of the normal vector on both sides. Oops, magnitude of the normal vector on both sides. And then hopefully what you can see is the right side, that magnitude n, magnitude b, cosine of theta, is the same thing as the dot product of n and b. So on the left side, I get the magnitude of n times d times the dot product of n and b. And now I can go ahead and solve that one for d, which is going to be the dot product of n and b. That looks like a minus sign, should be a dot. Still looks like a minus sign. Make it a bigger dot. There we go. Over magnitude n. And you'd be right in thinking, well, hey, that kind of looks like it's a component. It's exactly what it is, actually, in this case. But yes, it does look like a component. But ultimately, we're going to use that to be able to find a good equation, or an easy equation, to find the distance. So d itself can be written as the dot product of n and b. So let's find the dot product of n and b. So that's going to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught over the magnitude of n. But the magnitude of n is just the square root of each one of n's components squared, added together. Okay, it's actually a pretty good formula, but we're going to simplify it even a little bit more. If I was to go ahead and distribute now the a, the b, and the c in the numerator, what we're going to get is ax minus ax naught plus by minus by naught plus cz minus cz naught. Again, all over the square root, because that's the magnitude. And then what I'm going to do is I'm going to reassociate some of the things in the numerator. So now we're going to have ax plus by plus cz, and then minus. Now I'm going to basically just take the minus out of the other three, so that I'm going to get ax naught plus by naught plus c z naught. Again, all over the square root. All right, and hopefully you can see. Hopefully you can see what I did there. This part right here, that part right there actually lies in the plane. Because what you have there is you have an equation, ax plus by plus cz. The only difference is we plugged in x naught, y naught, and z naught. So again, the general idea here is that x naught, y naught, and z naught, that's a point in the plane, is in the plane. That's the one we kind of started off with up in the top. That's p sub 0. So from that perspective, since it's in the plane, it must satisfy this equation because it's in the plane. That is the equation of the plane. And since that point is in the plane, it must satisfy the equation. So what I can write then is that a times x naught plus b times y naught plus c times z naught plus d equals 0. That has to be true since it's in the plane. Or what I can do is I can rewrite that as ax naught plus by naught plus cz naught equals negative d. Well, that gives me something now. I can replace this negative d for that whole thing right there. So my final equation is that d, or the distance, is ax plus by plus cz plus d over square root of a squared plus b squared plus c squared. Now, how do I get that plus d? Remember, I was subtracting a minus d. That's how we got that. And it is a distance, and it is possible that this thing here gives you a negative. So we throw in an absolute value. You can call it a magnitude if you want to, but remember, everything that you have on the inside of that's going to give you just a number anyway, so there's nothing to take the magnitude of. So just make sure that your distance is positive. This right here is the formula that you're going to use. It was a lot to develop that formula, but at least now you have an idea where it comes from. So really what you need is that normal vector, because that's your a, b, and c in order to be able to do this, and you're going to need a point. All right, let's go ahead and do the first example. So example 1 says find the distance from the point 285 to the plane x minus 2y minus 2z equals 1. Okay, this one is actually really, really simple if you have the distance formula, which we now do. According to our distance formula, it is a times the x value. Well, here is your a, b, and c, so let's go ahead and write our normal, because that's going to give us a, b, and c, so that's going to be 1, negative 2, negative 2. So now we have a, b, and c, and obviously this is x, y, and z. So it's ax, so it's going to be 1 times 2, plus by, so really that's going to be minus 2 times 8, plus cz, so it's going to be minus 2 times 5, plus d. Now be careful on this one. D itself is not that. Remember that that represents negative d. So negative d here is 1, which makes d negative 1. So it's really minus 1 on the top there. And then, really the easier part is the square root part. So we get 1 squared plus negative 2 squared plus negative 2 squared. And then we'll simplify. So we're going to get, what is that, 2 minus 16, so that's negative 14, minus 10 is negative 24, minus 1 more is negative 25. And then the denominator is going to be the square root of 1 plus 4 plus 4 squared to 9, so it's 3. And you see how we got a negative value. That's why we use the absolute values there, because the distance between that point and that plane is 25 thirds. All right, let's go ahead and do the distance between the two parallel planes, and then I think we'll probably come back with a second video and finish this off. All right, so if I want the distance between two parallel planes, the idea is pretty simple. I've got the normal vector that I need for either one of them. So you just have to pick which one you want to have the normal vector. In this case, I'm going to pick this one to have my normal vector. So I'll have the normal vector come from there. It doesn't really matter, by the way. So we'll say it's 3, 6, -3. That's my normal vector. But that's coming off of the second plane. So what I really need is I need a point that's on the first plane. Okay? How do I find a point on the first plane? Well, it's actually pretty simple. Let's let x and y equal 0. Why not? So we can let x equal y equal 0, because if that's the case, if I plug 0 and 0 in, that gives me a z value of 1. Well, that point lies on the plane, so now I have a point 0, 0, 1, and that point comes from that plane. So I have a point on the first plane, I have a normal vector from the second plane. Now we can find the distance from that point down to the plane on the other one. So now we'll just plug this stuff into the distance formula. So again, our distance formula says ax, so it's 3 times 0, plus by, 6 times 0, plus cz, -3 times 1, plus d, and d in this case is -4, so it's, I should have just written -4, over square root of 3 squared plus 6 squared plus -3 squared. So let's see, we get 0 plus 0, -3 -4, so we get -7 on top. And the denominator is going to be 9 plus 9 is 18 plus 36 is 54, so square root of 54. And then we'll just make that positive, so it's -7. I'm sorry, not -7, I want to make it positive. +7 over root 54. And that does simplify a little bit. What can go in there? 9 can go into 54, so that's going to be 3 root 6. And if you really wanted to rationalize just to make it more proper, you could multiply the top and the bottom by root 6, but it is not necessary in this case. This is perfectly fine. All right, let's come back with a second video and we'll finish this up.